Okay, here we are back. The idea is we're on the second part. We're doing compound interest now. We are going to see how Boris's debt of 32,000 accumulates in a compound interest situation. So we have the standard compound interest formula. Thankfully, this gives us the amount of debt that's a total value of the debt at any moment in time. So we don't need to do the two-step process that we did with simple. Right? Didn't mean to do that. Now, in this case, P, the principal, the original amount, still 32,000. R, the interest rate as a decimal. Again, I'm using the same interest rates as we did for simple interest. So it's 3%, 3 over 100 as a decimal, or 9 over 100 as a decimal, or 15 over 100 as a decimal. And from there, N can be any value. Right? And because here, that's our years. After 0 years, 1 year, 2 year, 3 year, 4 year, 5 year. So here, 32,000, we still start the same amount. Right? So in our formula, P is going to be 32,000. R is going to be whatever it should be for the appropriate row. And N is going to be the number of years up here. So essentially what I'm going to be doing over here is plugging values into that formula. 32,000 times 1 plus, I'm going to look at this cell first, right? That cell there, it's 3% there, so it'll be 3 over 100. And it's going to be only to the power of 1 because it's just at 1 year. And there we go, we get 32,960. That should be the same as we got for the simple interest. So those actually should be the same for the first year. The values should be the same. I could cheat and copy them, but I won't. To find out future years at 3%, all I need to do is change the number of years up the top there. So we'll get 33,948.80. Whoops, that wasn't a dollar symbol. And keep doing it. Keep pressing the back button on your calculator. Change it to the next year. 34,967.26. Change it to the next year. 36,016.28. By the way, would you expect these compound interest values to be higher or lower than the simple interest ones while I'm doing all this? Can only hear the sound of the kids in the background, not giving much away. Look, compound interest, these amounts are going to be much bigger because he's going to end up paying interest on top of the interest he's already earned. It ends up being quite a lot. I'm now going to do the 9% row, so I need to change this 3% to 9% and start again at 1 year. So we're going to start at 34,880. At 2 years, 38,019.20. At 3 years, 41, 440, 93. Remember to round to the nearest cent. I always round to the nearest cent in case you haven't noticed. 45, 170.61 at 4 years. And at 5 years, 49, 235.97. There we go. Now I need to do the 15% row. So what needs to change here? The interest rate. It's no longer 9%, it's 15%. After 1 year, 36,800, as I remember we had for the simple interest after 1 year. Change it to 2 years, 42,320. 3 years, 48,668. 4 years, 55,968.20. 5 years, 64,363.43. You can see the sheer power of compound interest here. Do you notice that at 15%, it is doubled. It is more than double now what the original amount was. Compound interest is brutal. It's nice if it's your savings. It's not so good if it's your debt. I mean, compare that to the simple intersect, just over 64,000. Simple interest was at $56,000. Compound interest means it's more than $8,000 more at the same interest rate. I mean, that's interesting, isn't it? All right, now just to show you quickly, this is how we graph it. We're going to copy it, drop it into Excel. It actually needs a bit more space there. That's why it's showing all those hash things, because the cells weren't big enough to show the values. I go here, highlight it. Oh, I'm going to delete year because then Excel doesn't do as much stupid stuff. Here, insert, click a line graph. There we go. So this is Boris compound interest debt. And you can see what eventually happens here with any sort of compound interest is it eventually forms an exponential function. The rate of increase keeps increasing. So if you think of this, it would keep going way up like that. In fact, while I'm here, because I know you desperately want to see this, I might show you what happens in the long term in a few more years. This is a bit of funky Excel stuff I'll do here. If I actually wanted to find the, using the compound interest formula in Excel, I could write equals 32,000 multiplied by 1 plus 3 divided by 100 to the power of that value there. And I can copy that formula, and I can copy it here, and I can copy it here. For 9%, it needs to be 9 divided by 100. For 15%, this is really extension here, guys, but hey, let's have some fun. Now, the good thing is once I've written this formula here, because it's referring to the cell H20, it's referring to this 6. If I just copy that over here for a few years, oh no, I need to change the numbers, that's not going to work. It's actually going to show the amount of debt for however many years we want it to go out. There we go, 28 years. If Boris continues not to pay anything and ask for trouble, look at that. At 15%, after 28 years, he owes $1.6 million. So compound interest is remarkably powerful over long periods of time, particularly if you have bigger values. So I'll just graph that. I'll just highlight the new graph. And check out that pattern. That is a very typical pattern that you see with exponential growth, and compound interest is an example of that. That's extending things beyond what you need to do, guys. What you need to be able to do is you need to be able to create that table of values back here. You need to be able to do these calculations and create these tables for compound and simple interest. You need to be able to copy it in, you need to have it in Excel, and you need to be able to form a graph. That's all for today. Thank you. I hope you're having a fantastic time wherever you are.